we'll get started. I think it's maybe 10 minutes late already, but I'll go fast. I speak fast. So I'm TJ. I'm going to talk about fixed wing planes today. It's a platform near and dear to my heart. Specifically, some new features in PX4 that we're trying to improve the performance and safety of flying in strong winds with. So dive kind of right into it. Sending planes, especially fixed-wing planes, you want them going far beyond visual line of sight often for missions, out in the wild on their own. You're supposed to operate autonomously. And I don't know, maybe you get into situations like this where you have random terrain winds coming out of a fjord and grabbing you 60 degrees to your flight path, or I don't know, maybe coming down for a landing. Strong rotor from a hill from behind the camera here. This is all controlled with PX4 in the past, I have to say, but really scary kind of flight, right? And even in the worst case, some smaller planes may even go backwards with respect to the ground. Just can't keep up, right? So kind of the point of this is, what do we do in these situations? They're not as uncommon as you might think, especially for small, slow-flying planes. And so there is some guidance law that's been on PX4 for some time, and unfortunately it doesn't do the best at handling these situations. So on the right you can see here just trying to follow an orbit with 14 meter per second wind with a 15 meter per second cruise speed. Path is quite off, but the bigger concern here is jumpy set points. So airspeed commands kind of jumping up randomly, roll set points getting very oscillatory, even a bit divergent at a certain part. And this is mainly due just to a kind of simple thresholding logic that's been there in the past. So it's obviously not the nicest thing for us. What would we actually like to do? Well, we'd want something a bit more repeatable, predictable, so intuitive. If you look at the plane, you understand what it's trying to do and why. We also don't want these jumps in the controls, so no more switching logic, no more oscillation, and ideally we don't want to use too much energy while we're flying and trying to combat these winds. So efficiency is a concern here. So how in this talk will I show how we've tried to do this with some new features? First, coupling heading and airspeed set point logic, which I'll dive into here in a second. And then second, we have an onboard wind estimate. Why don't we use it? So those are the two main things that'll hopefully make things a bit safer for our fixed wings here in the next few slides. So just to set up the problem, get a little academic, only for a little bit, I promise. So we have an airspeed, we're flying in 2D, let's say. This is our plane. And once we enter a wind field, this shifts our resultant ground velocity. So simple stuff, but let's just follow the diagrams as we go through. This is that weird case now with that small plane flying backwards with respect to the ground. So this can happen, does happen. This is what I call excess wind. So we have some cone now where, let's say I want to command a bearing. So where do I want the plane to go? In this cone, I can actually achieve this. Outside of it, I can't achieve it. And this is, again, the situation that wasn't handled before, is handled now. So how do we handle it? Directional guidance, it's actually quite straightforward geometry operation here. What we normally do, we have some path we want to follow. We take the closest point on that path and then command some kind of look-ahead vector for the aircraft to follow. So this is where that bearing comes from. Then we get a course error, so from our ground speed to this direction we want to head, and this can give us some kind of steering command for the vehicle. So that was the past. What we could do if we use the wind estimate is just directly connect this triangle with an airspeed reference. So then we get the exact resulting ground velocity that we want. And you'll see here in a second how this will lead to continuous roll and airspeed commands and kind of protect us against these strong winds. So this gives us a heading error, not a course error anymore. So now let's look at this infeasible, or let's say the wind cone here. So this is again with this wind that's greater than our airspeed. Inside the feasible cone, we can keep connecting that triangle, getting that heading error, and we can always track the bearing. So this is an ideal tracking objective. Once we exit the cone, it's not so ideal. We can't follow the bearing anymore. It's just not physically possible. So what are you supposed to do in this situation? Well, if we just follow the circle all the way back, we can end up in a safety objectives. So this will, in the worst case, minimize the rate of deviation from bearing. So this is basically how do you mitigate a runaway of an aircraft in the very worst case possible, where you want to reduce how fast you're running away from a path. So we'll hopefully try to avoid this situation. This is obviously not increasing in airspeed here, so how do we avoid it? Obviously, go faster, right? But now about efficiency, how much faster should we actually go? So this is now where a new part of the guidance logic comes in. So efficiently increasing airspeed, let's say we have some desired speed, or there's endurance, range optimal for cruise, that's our orange circle. We also have a maximum airspeed. Generally, there's some extra allowance for our aircraft. And then we have this space to play with. So where should I set this airspeed reference within this extra space? It turns out, again, very simple geometry solution, take the right triangle, and we get the minimum increase in airspeed necessary to follow that bearing. Another thing that's nice is if we have some minimum ground speed we want to track, we can just shift this vector along the bearing line, and again, minimum increase in airspeed necessary to have the bearing we want at the ground speed that we want. So does it actually keep all of our commands continuous? So this is all the logic I just showed with different bearings circling around. So that green and red vector is just the bearing. Wind increasing. Here in a second, minimum ground speed will increase. Everything variable, and we still get no jumps in our logic, which is what we want for a nice behavior of the aircraft. So it's on PX4 now, so how do we use it? This is the library, which is called Nonlinear Path Following Guidance. It's very generic. It's now on v1.13. It's optionally enabled, not by default, but I encourage you to please use it, and let's get it in testing. And so it's only for fixed wing modes currently, and this is the parameter you'd need to set to enable it. So the wind-aware features, obviously we need a valid wind estimate to actually use these. So for a fixed wing, generally that means you should use an airspeed sensor or have a nicely tuned estimator, for example, including this side-slip fusion. You need the wind estimate or else the wind-aware guidance isn't going to work. So then how do we tune it? What's nice is it's derived such that you can set explicitly the period or the damping ratio. So controls people out there, you choose the control response behavior you want, or the dynamic behavior you want. Legacy L1 parameters can be directly transferred, so they map one-to-one. And then for those who haven't tuned this kind of a controller before, lower period is more aggressive. So on aggressivity, how do we know if we've been tuned too aggressive? You might start drawing nice pictures like this flower here if you have too low of a period gain. But a nice new feature we have, if we enable, is automatic tuning stability adjustments. So then it will correct it for you if you put something too low. So what is that actually doing? It's an adaptive lower bound to the period that'll keep us from oscillating or diverging. So this is in that example you just saw. A really, really low period, probably way too aggressive, 3 seconds was set at the beginning, and then the algorithm adapted it on its own up to this higher period to make it stable. This is how that can be enabled. That's the parameter in PX4. But of course, there's no free lunch, so we have to do a bit of legwork for this to actually work properly. And that's another parameter to set, which is this roll time constant. So what is a roll time constant? Basically, this is our response dynamic from a roll set point to a roll response from the vehicle, so our roll attitude loop. So how do we identify this? So the first thing, you can set log into high rate if you're going to go fly. Fly in an altitude or stabilized mode. Make a bunch of maneuvers, so hard lefts, hard rights. So this is then that roll set point, roll response. So roll is how the aircraft's actually steered. That's why this matters. And then if we fit a first order transfer function to it, we have our roll time constant already, and we can apply this directly. So this is how the algorithm is able to know what kind of stability margin it has given the period that you set. And the path constraints, the wind condition, everything. It's all baked in. This was, by the way, just a hobby plane. So this is real flight data from it's a Trojan T28 from E-Flight. So that's what it would look like. I'll upstream a script, Python script, to do this for you, hopefully in the next week or so. but then you can set your time constant. So now these new wind behaviors. So what do we want to do in these cases with very high winds? There's a couple options now, again, with parameters that you can set. So let's say we have a path we want to go to. We have our vehicle with a cruising airspeed, some wind that's now greater than the airspeed, so we're at negative ground speed. What to do? So the first option, we can set a minimum for ground speed. That was something that existed before in PX4, but with the new logic, it works just a little differently. You can choose with that parameter what ground speed you want as the minimum. This is a forward ground speed, so that means with respect to the body axis, we want to be moving forward. And then basically we just increase the airspeed. This is what the algorithm will do to get back to the track. And it will always try to at least maintain that minimum as it moves forward around the path. So back to our example with the legacy guidance where this wasn't working so well. This is what it looks like with the new guidance. So we have nice, smooth, continuous roll commands and also airspeed increases. And we actually do track the path, which is nice. The other option, which I actually like a bit better, it's maybe a bit more efficient, it's called track keeping. So this is the parameter to set for track keeping. And the other thing you need to do for this one is set the minimum ground speed to 0. And so the reason for this is that we'll increase the airspeed to return to track in this mode. And as it's returning to track, this other parameter here, this is the maximum ground speed it'll command when it's very far from the track. Once it gets back to the track, it actually reduces the ground speed aid to 0. So then in this wind condition, we'll literally sit on the track at 0 ground speed and just wait until the wind goes away. So an example of this, I have a flight experiment for you. If it will start here. So this is up on a mountain near Zurich called Uetliberg. So again, the idea here is we want to get back to the track and just sit there and wait until the wind gets safer. So this is just a little easy glider hobby plane. And the wind's like 10 meters per second or so, going up and down below and above the airspeed that's nominally set. And then these green lines there are 1 meter track offset from the path that we want to follow. So the algorithm basically brings it back to the track, tries to sit there as well as it can while there's gusting, and we're able to stay. So what do we improve? Repeatability and predictability, I believe, is actually quite well improved. So it has very specific behaviors that it will follow and always react the same way. Control continuity, that was shown as well. So we don't have any more switching logic, no more jumping controls. And then efficiency, this is literally the mathematical minimum of airspeed you can add for these different given conditions. And as a bonus, we get this safety and stability from the automatic stability bounds. And also the algorithm is just a bit more general from L1, so we can follow paths with variable curvature in the future. I would like to push the community there as well. And so for the outlook, what would be nice is if we had an independent wind estimator or filter specifically for the high-level control feedback. So right now, on PX4, on 1.13 release, it uses EKF2's wind estimate. Normally, that's tuned quite kind of like a DC signal, so it's very stable over a long time, but it doesn't capture these small gusts. So for the flight test you saw in the last video, I actually had tuned this EKF2 wind noise gain to maybe an order of magnitude more than what it normally is, such that these 2 meter a second gusts are captured. What would be nice is if we don't have to do that, but we have a separate wind estimator just for the high-level guidance law, and then we can filter it as we like for whatever behavior you'd like to do. Then path following interface. So I'd like to get away from waypoints and just use paths. That's what fixed wings like to follow. So we're trying to go that direction now, but anyone who wants to help, please. Then this algorithm is quite generic. So VTOL multicopter could also do path following with the same algorithm. So it'd be a nice thing to experiment with as well. And then I don't know if PX4 actually has that many surface vessels or submarines, but if you can imagine a boat going down a river, that's actually exactly the situation where a flow might be stronger than the speed of the vessel. So it'd be interesting to apply this algorithm there as well. So go fly it, please. Let me know how it goes, and I can answer any questions if you have it.
Yep. Could you elaborate on what the current switching control is like
Sure. So, I mean, basically, it's not, let's say, the fault of L1. L1 is designed a specific way, and right now there's just kind of a Band-Aid on top. Or not right now, let's say in the past there was a Band-Aid on top that just said, here's a 3 meter per second ground speed threshold, and below this, with another kind of arbitrary angle condition, we just blast some throttle and have this ground speed undershoot. The problem with this is these intersections of the conditions, the thresholds, made this jumpy behavior as it was flying around some kind of path. So the reason probably people haven't complained about it too much is I guess people don't fly in this much wind that often. But if you do fly in this much wind, it becomes very obvious very quick that we need to fix it. So that's why this algorithm has been implemented. So sorry, L1. L1's just, it's another path-following guidance law. Another thing I'll mention is that this new path-following guidance is almost identical to L1 in most situations. So if you've been flying fixed-wing vehicles on PX4 for a long time, you won't see a difference if it's in normal conditions. This is exactly, it's just an abstraction of the path-following guidance law. So it's not changing things in general. Again, the same gains can be translated. Everything works the same. The only thing that's different is you get the advantage of these high wind handling scenarios, assuming you have the wind estimate.
Do you derive the wind estimate from the aircraft, or is it based on the ground estimate? Where are you getting it?
So EKF2 has a wind estimate on board, and there's also another standalone wind estimator on board that's not being used for this algorithm right now. But both of them, they basically just fuse ground speed from GPS, so GNSS velocities, the airspeed from a sensor, so a differential pressure sensor converted to airspeed, and then the headings from your magnetometer. So with these three things, you can already reconstruct the wind. And of course, with some acceleration as well in the estimator, this can help to get things narrowed down a bit more, because mag's a bit noisy. But in general, I mean, those are the three things you need. So magnetometer, or if you have, let's say, two GPSs that are tightly synced, you can also get heading this way. But if you have a heading, airspeed, and ground speed, you can get the wind speed from this. The synthetic side-slip fusion is another way that helps in kind of nominal conditions, as long as you get a little bit of excitation. So what that does is assume that planes generally are designed to kind of fly straight and forward. So there's not that much slip. So slip for an aircraft is when you have kind of an angle to the incoming flow with the body axis. And so if you assume that's normally 0, you can inject these synthetic measurements in the estimator, at least something close to it, and then this constrains the problem a lot for the estimator, so you can then also get a wind estimate out of it. So that's also something that's on PX4 and available if you don't have an airspeed sensor. I prefer airspeed sensors still, it's safer to me, but that's maybe a conservative talking point, so.
For other craft, have you tried any, because meteorology, there's wind sensors, ultrasonic, bunch of others. Have you tried anything like that?
Yes, so I wouldn't recommend, honestly, using a ground sensor for the wind if you're going to feed it to this level of control. So this is like a high-level control law, so just position control. But the issue here is that you actually want to capture these kind of 1-2 second long gust events that might go 2 meters per second up or down. And with a ground wind sensor, maybe you do capture those, but it's also not where your plane is, right? So it's another thing that, especially with terrain, when you're flying below 150 meters, which is what most regulations require, terrain-induced effects on wind are very significant. So you fly next to a hill, you get a strong rotor, your ground sensor's over here, it's feeling clean air. So it's not as helpful as having that onboard estimate. Oh, okay, sorry. I thought you meant like the kind of ground ultrasonic stations. No, yeah, I mean, ultrasonic, I haven't tried an ultrasonic on, actually I had some students a while back who were looking into an ultrasonic sensor to put on an aircraft. I never saw the results of it. So if that exists, that'd be nice. I'd love to test it. Yep. So I have to say I'm not that well versed in how these ultrasonic sensors work. Yeah, if someone here is, please let me know. But yeah, I guess it depends on what it's measuring, right? So if you're, I don't know, maybe I'm getting this wrong. An ultrasonic sensor is kind of looking at the feedback from some light, right? And then it determines what kind of vector the flow is at somewhere else. Somehow you'd have to fuse this. I'm not exactly sure.
I don't know if they work in the air. Because they're kind of expecting even flow all around, but flow around the station. That's how it's kind of funny.
Yeah. A good trusty pitot tube does a good job. So, yep.
How does the path following interface work with the mission control logic?
This is exactly what I want to change. So right now, it's all kind of waypoints, mission items, and the paths that the guidance law, so L1 or NPFG, the new one, follow are actually just constructed kind of ad hoc from these waypoints and mission items. And that's kind of the issue, is there's all these kind of convoluted logics to how do I determine with these 3 points what path I'm actually trying to follow. We should just follow a path. Here's a line. Here's an arc. Here's a Bezier curve, whichever thing you would like to do. But this will require some interface design, right? So another thing, we don't want to kill legacy setups. So let's say there might be like a mission deconstruction interface that needs to be there. So you would take a mission set as it is now, do the same reconstruction, pump it into some paths that we can feed down to the controllers. But in general, I mean, let's say ideally what I'd like to see, send a line, send an arc, send some Dubbins curves. This is a very typical thing for aircraft to follow. And then we know exactly what we're actually trying to follow. So if you look on QGC, you'd see a line, you'd see an arc, and that's exactly the path that we actually want the plane to follow, and it's trying to do it.
And with the track feature that you just talked about, does that mean that instead of like flying circles around a fixed path, you can now follow a point like within the mission?
So it depends on the wind for this. I mean, so actually something I haven't tested yet, but I would like to very soon is, let's say for a VTOL or a multicopter that's flying much slower than maybe the wind might be, or even with no wind, this algorithm actually can go down to 0 airspeed without braking. So what you could potentially do is basically command a 0 ground speed, and then it will try to get back to the track and just stop, right? So the track keeping could be used in a mode where the nominal airspeed is 0. It's a bit of an odd situation for like a unicyclic kind of guidance law like this, but it's possible. So this track keeping, though, as it was shown there, it assumes you're flying at some speed, right? And that there's enough wind that you would actually stop there and not increase the speed anymore. If there's no wind, you'll keep following. It won't stop.
Hey, I got a question from Zoom.
Okay.
Is this algorithm implemented directly in the firmware or in some other high-level layer?
No, it's there. It's there for 1.13. All the parameters that I showed in the slides, that's how you enable it. You can clone it now, put it on your plane, and try to fly it.
When are you going to write the tuning guide?
Yes, thank you for that question. I actually wanted to have it written before this talk, but I was a bit distracted. So yes, thank you for the nudge and the poke. Please keep poking and complaining, and I will write it. I'm hoping these slides, I'll upload these as well today to the schedule. And these already give a little bit of documentation, but I'll put the proper one for you, Hamish. Thank you for the poke.
Yeah, I've got a two-parter, I guess. How much improvement do you expect to see on like a quad rotor setup, and what does the implementation path look like from where you are to that?
That's a good question. So again, the quad rotor stuff, I haven't tried yet. This is something I would like to try, so this is speculative. I'll preface this. But so one thing, I think quad rotors, there's no reason they can't use path following. It just means that you would set some speed you want to go, same as it was here, and it would try to go to the path in a similar manner. Tuning it maybe would be a little bit different than it was for the fixed wing, so I don't know the answer to how it looks for tuning with this exact algorithm. The other thing is, so for example, on the multicopters for PX4 now, there's this jerk-limited trajectory generation. The library, this velocity smoothing library that is used for that jerk-limited trajectory generation, this actually has the tools already needed to, for example, from any point check, let's say if you have a path, and I'm so far away, what's the max velocity I would need to converge to that path with a certain limited jerk and acceleration? We could even use this as an enhancement to the algorithm. So instead of just being, right now there's a velocity-dependent term for when the aircraft starts blending into the path, whether going perpendicular to it or going into the path. For a multicopter, you could even implement this jerk-limited boundary of when it starts turning into a path. But like I said, it's speculative stuff. I don't know exactly what other issues will arise when trying this out, or what multicopters would actually want. It may be that the behavior you want for a multicopter is not the same as what it has here. Yep.
Ask some questions about, I guess, how it was working in when you were getting to the track and then trying to pause. There were some moments where it went ahead, and then it kind of, I guess, slowed down and moved back. Are you, I guess, leveraging the ability of the airplane to move backwards? Are you sending negative ground speed commands?
I have, okay, so there's two parts to this. I have a backup slide exactly for the second part of this point, which is a fun kind of animation. But to the first part, when it was going kind of back and forth on the path, this was actually just wind increasing and decreasing. So the airspeed was being kept just about constant, just with small increases and decreases, but with gusts. So let's say once it got back to the path, we had equal wind speed and airspeed. It's sitting at 0. If the wind lulls a bit, then of course it's going to go forward. If the wind increases a bit, it's going to go a bit back because it's a feedback law. So it has to get the measurement and then react to it. So that's most of why it was kind of going around like this. That's kind of inevitable. The other part, so I think this is what you're asking. You can tell me if I'm wrong here in a second, but there's actually two solutions to the airspeed vector problem for this negative ground speed situation. So the one chosen with this algorithm is always the faster one, but you can also tell him to go backwards if you want. So this is an example of the algorithm either using a forwards or a backwards command. So you could tell the plane to literally go backwards onto the path, something I tried as well. It's not on the PX4 version, unfortunately. I took the other one because it was a bit more straightforward and maybe intuitive, but this is something I could add if people are interested in. I've flown it before. It's actually kind of fun to watch the plane turn around and go backwards to a path. Yep.
Got another question from Zoom. For a quadrotor scenario, would you expect the algorithm to handle turbulence caused by the vehicle when flying near objects rather than wind gusts that are independent? Is there a chance of getting into a feedback loop in this case?
So asking about it responding to turbulence. So the thing is, if there's a wind estimate being used for the algorithm, it's probably a filtered one. So if there's, let's say, smaller turbulences, I kind of doubt the estimator will pick these up that quickly. And so that won't be fed back to the algorithm. If the platform is deviating a bit because of small turbulences, this is probably going to be more on the ground speed feedback part of it. Or on the attitude level even, if it's that low level. Yeah, again, the quadrotor case, I'm more speculative here, so I don't have the best answers for this.
Okay, that's time.
Okay. Yep, well, thanks. If anybody else wants to talk more, I'm around.